Electric field of continuous charge distributions. So the general method for finding electric field of a continuous charge distribution is this. Divide the charge distribution into infinitely small elements dq. Express the charge element dq as either lambda ds for charge distributed over a line, or sigma dA for a charge distributed over a surface, or rho dV for a charge distributed over a volume. Choose an arbitrary charge element, write the magnitude of the contribution of the E field at the observed point dq as if point P as if dq were a point charge. So dE will be equals to k dq over r squared. Then find the total E for the entire distribution by integrating. So first off, we will try to find a uniform line, the electric field due to a uniform line of charge. Now what do we have to do in order to do this? Now we have to find the electric field due to a uniform line of charge. Okay? This is going to appear very similar to the one that we were dealing with in the last chapter. So you have a line of charge. Let's suppose it is a positive charge. And we want to find that there is a test charge here, dq, and we want to find the electric field due to this line charge at this point. Okay? And let's suppose that this is a line that's sort of in the center. So I'm just going to move my dq here. So how do we do this? Well, first of all, because this is a line charge, because this is a line of charge, it is going to have a linear charge density which is equals to Q over L, where Q is the total charge and L is the total length. Okay, so that's something that we know. Okay. Next, as we talked about it before, we are going to divide this line of charge into smaller volume elements, dq or dz each, and each will have a charge dq. So this is dz, and it's each going to have a charge dq. Okay? Then we have to come up with our coordinate systems, right? So our coordinate system, as I choose it, it's going to be y, z, and x. Okay? So x is going to be pointing outwards, y is this way, and z is that way. Okay? Now we have to find the effect of this E field on this positive charge. So now this is going to be, this is a positive charge, my test charge is positive, so my dE due to this small volume element is going to be pointing in this direction. Okay, so that's good. Now we have to figure out what are the different, what is the total electric field. So first of all, we're going to try to see which field actually contributes to the electric field at this point. So we'll start with EX. So EX, electric field along the E direction. Well, we know that this is perpendicular to the page. So this means EX component equals 0. Now what about EZ? Well, if there is a volume element here that contributes dE to this point, there has to be a exact same volume element here that contributes to the other side. So EZ goes to 0 from symmetry. Okay, they cancel each other out. So we are only left with EY. So EY exists. And what is DEY? So DEY will be DE cosine theta if this angle is theta. Okay? So if this angle is theta, then I can say this volume element is Z away from the center. This becomes Y and this becomes R. So cosine of theta is actually given by Y over R, and R is equals to Y squared plus Z squared. Okay? That's from Pythagorean theorem, right? So this means if I place the values in here, okay, so this is what I'm going to be left with. Now, I know cosine theta equals that, but what is dE? dE is actually equals to k dq over r squared. Okay? This means, oh, and dq is going to be lambda dz over r squared. Okay? Why? Because for the small volume element dq, that is going to be equals to dz, which is a linear charge density, divided by dz there. So once I have that, I can rewrite those in here. So dE equals that. I can place that value in here, and then I can also plug in the value from cosine from here. Okay? So I'm just going to get a blue marker. So my dE will become k lambda dz over r squared, and cosine theta will be y over r. I can simplify it, k lambda dz y over r cubed, which I know is going to be y squared over z squared 3/2. Okay? So dEy becomes equals to that. Now we had to calculate EY, right? So in order to get EY, I have to integrate both sides. So it'll be k lambda dz y divided by y squared plus z squared 3/2, and that's going to be integration. So what am I going to get? I am actually going to get E on one side, right, equals k lambda y integration over dz divided by y squared over z squared 3/2, right? And what is the limits of this integration? Well, the limits of this integration are going to be minus L over 2 to L over 2, because this is going to be in the center. So my limits of integration are minus L over 2 to L over 2. Now how do I solve this? That answer is going to be given in appendix, I believe it's appendix 1. Okay? Solve it. Put the values in here. I'm going to not spend too much time doing that. But you will get E equals to k lambda L over y square root y squared plus L squared over 4. Okay? That is the electric field due to a uniform line of charge on a point here. Now, in the limiting case, where y becomes really, really large, so this point goes really, really far, and this line stays here, and y becomes really, really large. So when y goes to infinity, we see that this equation gets reduced to E equals k lambda L over y squared, because y will become much, much greater than L. So this is what we're going to get. And if you want to think about it a little bit more, this lambda L is equals to Q. So I can plug those values in here, and I get E equals k Q over y squared. Okay? Which is like 2 point charges.